data management and probability. So this is a test. Okay, so once you kind of finish up with the combinations chapter, you may want to be able to test yourself. So just as usual, what I'll do in this video is I'm going to go over a set of questions. So there's about 7 questions in here on this particular test. I don't know how many you typically might get. You might get some more, but this will be a good test for you. Okay, so I will put a link to the PDF file of this test so you can grab it on your own and then solve the questions as you like. So you'll see that in the show notes. And let's get started. Okay, so question number 1. So there are 12 qualified officials. And so there's 2 parts to this question. Part A states that we are being asked if we do have 12 officials and we have to fill 5 positions are to be filled where all the officials I guess are qualified, then how many different possibilities are there? So this isn't a very hard question to be able to solve. But I find what I struggled with when I was doing always this is when do I use permutations, when do I use combinations, when order matters and when order doesn't matter. Now in this case, order does not matter because they're saying, 5 positions are to be filled with an official and they give us 12 qualified officials. So they don't state anything in particular in here. So to get an answer, this would simply be 12. Choose 5, and then that is it. And of course you can find out what this is on a calculator, or you can just do it in the old-fashioned way. So this would have been, 2, so 7 factorial, 5 factorial, and then whatever the answer here is. So I'll leave that with you. I guess the main idea is, okay, so what do I use? And this is just 12 because we have 12 officials, and we're choosing 5 different positions, okay? And then the order doesn't really matter, okay, for this. Now, in part B, it says if a starter, head lane timer, stroke judge, turns judge, and a clerk, of course, so this looks like it's swimming, for those who may know, and for those who don't know, that's okay. So there's different positions, but they're in particular. So if these to be filled, then how many different possibilities are there? Well, because of the fact that we do have now a starter, so this is part B, so we have a starter, we have a head lane timer, we have a stroke judge, we have a turns judge, and then we have a clerk, of course. So those are 5 different positions. Now, imagine you didn't even have 12 officials, that you only had 5 officials. So if you had 5 officials, right, so you have 5 different positions, that in order to fill this, so order does matter because one official can be a starter and then another one can be a clerk, of course, and they can swap and so on. So we really have 5 different things that we want to be able to fill. So if we only had 5, we would have said, okay, so that's 5 multiplied by 4, multiplied by 3, multiplied by 2, multiplied by 1, which is just 5 factorial, or 5p5, right? Now, here order does matter because we have different types of positions. When the positions are irrelevant, then order is irrelevant. It doesn't really matter who fills which. But as soon as you do make them have a particular position that they have to fill, even if you had 5 of them, you can rearrange those 5 factorials, I guess 120. So that's a lot of different ways that you can do that. Now, if you have 12 qualified officials, then this would have been 12p5. And then whatever that answer might be, you can find that out. So parts A and B are actually different. Now, in the case, if these 5 positions were particular positions like they were here, then we would have had to do 12p5 for part A. But because they didn't state anything, they just said 5 positions. So I guess it doesn't really matter how we fill them in which particular order. So that's why I wrote 12 choose 5. All right, for that one. So that's question number 1. Here's a nice question. So given a number, so this is 8,820, they're asking us how many divisors does the number have? And then how many even divisors does the number have? Well, so it's interesting because how would we do that? Are we going to be just finding all the divisors of this particular number? Is there a particular way that we can save some time? And it turns out that there is, actually. And if you have studied counting, so permutations, combinations, things of that nature, then you can use this kind of thought process to see how many of these. So typically, okay, if you remember, any number, at least a whole number or natural number, it can be prime factorized, right? So I'm going to actually do that. So let me prime factorize this. Prime factorization, maybe I'll put up a link up above there for you so that you can take a look. Okay, and I'll do this in kind of fast forward fashion. Okay, so here's the prime factorization. So what you notice is you have 2 2s, you have 2 3s, you have 1 5, and then you have 2 7s. So in order to find all the divisors, right, all the divisors have to be some combination of these, okay? So, 2s, 3s, 5s, and 7. And what this comes down to is, okay, the kind of rule that when you have repeated items and then you're choosing from these items, okay, so for example, we can have, so there's 2 2s. So we can either choose one of them, we can choose 2 of them, or we can choose none of them. So those are three choices that we have, right? This is for 2. And then this is going to be multiplied by, okay, the number of choices that we have between 3s. And again, we can choose no 3s, we can choose 1 3, or we can choose 2 3s. So that's 3 choices once again. The 5s, well, we have 2 choices. We can either choose a 5 or not choose a 5. And then for 7, again, we can choose none, 1, or 2. So that's 3 different choices. So if you remember, okay, this goes back to basically counting the number of combinations that you have with repeated items, where you're interested in, okay, all the possibilities. Now, we're going to subtract 1 because that would be where we didn't choose a 2, we didn't choose a 3, we didn't choose a 5, and we didn't choose a 7, right? So if we don't choose any of those, okay, then obviously then there's nothing that we have. So I'm going to subtract that. But all the others, right, all the other possibilities, okay, that we have are actually going to give us the total number of divisors that we would have. And it's going to be quite a lot of them, okay? So if we would do this, so this is going to be, 3 times 3 times 2 times 3, I guess. So that's 54 different types of divisors minus, the empty set there, so 53. Quite a lot, right, that we would have. And that's how you can actually do and find out any number of divisors for any natural number, okay? So if you take prime factorizations, you can do that. Now for part B, it says how many even divisors does the number have? Well, finding the number of even ones would mean that we're including a 2, right? Okay, at least 1 2 or 2 2s. Okay, so you can do that. You can find out, okay, well, I'm going to include, if I include 1 2, what are all the possibilities with a 2? And what if I include 2 2s? What are all the possibilities? Okay, or the opposite. So what I can do to solve that question is I can say, okay, how many total number of divisors are there minus all the ones that don't have a 2, right, at all. Okay, so this is with no 2s, okay, because then it's not even. So, well, in that case, if there are no 2's, well, there's only one way to choose that, right? There's one way, okay, of not having a 2. And then you can just simply use these, okay? So if I take this, let me duplicate it in here. So this would be, I already know that the total is 53. So this is going to be 53 minus, okay? And then in here, well, this is 3 possibilities, no 3's, 1 3, 2 3's, 2 possibilities for the 5, and then 3 possibilities for this. And then of course I'm going to subtract minus 1 when there's that empty one there, okay, that I would have in here. So 3 times 2 is 6, times 3 is, I guess, 18. 18 minus 1 is, so this is going to be 53 minus 17. And then we can get our answer, you know, how many even ones that we would possibly have in here. All right. So I guess that's 10. That's so 43 minus, so I guess what is that? 36. So that's how you can approach this particular question. So total minus no 2's, right? Because as soon as you have a 2, then it makes it even, okay? So that is this particular example. All right, so here's another nice example. This has to do with, I guess, combinations. So you are doing an exam that has 15 questions. You are asked to solve 10 of those questions. So I guess 10 out of 15. The exam states that at least 4 questions must be chosen from the first 6. And in how many ways can you choose the questions so that you solve 10 questions as asked? Okay, so we have a restriction. So I guess, so 1, 2, 3, 4. Okay. So we have to choose, so it says, you know, 4 questions must be chosen from the first 6 that we have in here. And then we have to do 10 in total. So that means the remaining ones, so we have 1, 2, 3, 4, 5, I guess 6. That's from the last questions. So within here, we're going to have, so we're going to have, I guess, from the first 6, so at least it says, okay, so we have to be careful. So at least 4. So this is going to be 6 choose 4, right? That's if we had 4 of them. And then it's going to get multiplied by, well, we have 9 remaining, so 9. And then we want to choose, I guess, 6 of them, because that would be 10 in total questions. So this would be kind of case 1, where we have 4 from the first one. A case 2, we're going to have to add, what if we had 5 of them, right? Because it says at least 4. So that's going to be 6 choose 5 multiplied by, so from the remaining 9, we want to choose 5 from here. So we're going to be adding those up, you know, so whatever we get here, so equals, so this is case 1, case 1, case 2, so we're going to be adding those up. And then the last one, what if we chose all 6? Well, there's only one way to do that, but that leaves 9 choose 4, okay, to still choose from. And then we also would have to add this. So that would have been the total. So we can find what that is. All right, you can plug that into your calculator, okay, and compute this. I think that's within your range that you can do this. But this is a nice question and a nice thought process behind how would you approach something like this. So you do have to kind of break it down, because they said the exam states that at least 4 questions must be chosen. So that means it's 6 choose 4 in that first case. Okay, if you chose 5 of them, it's 6 choose 5, and then 6 choose 6. So we have to do a little bit of work. All right, so that's another question in terms of combinations. All right, so for this example, a family is planning to have 6 kids in total. Okay, so that's brave. And how many possibilities exist in the order of the birth of the kids such that there are 4 girls? And then how about at least 1 girl? Okay, so it seems like it's 2 different separate parts. All right, so if there are 4 girls, okay, so we have 1, 2, 3, 4, 5. They want to have 6 kids. So a boy or a girl is a possibility for each. Okay, so how could we possibly do this? So there's actually a few ways, right, that we can think about. We can list all the possibilities, which would take us quite a bit of time, and then see, all the different possibilities where there are 4 girls, right? So you can, maybe they have 4 girls right away, and then they have 2 boys at the end. Maybe they have a girl first, and they have 2 boys, and then 3 girls. So those are kind of all the combinations that we might run into. Now, there is a nice way of approaching this question if you do run into it. And it's using actually the binomial expansion, so binomial theorem. Okay, so if you remember when you're studying the binomial expansion, and then if you have combinations along with it, so with that Pascal's triangle and so on. So I'm going to write this like this. Okay, so you have really 2 choices, boy, okay, or a girl. I'm going to write BG. Now we want to have 6 kids, right? 1, 2, 3, 4, 5, 6. So it's going to be to the power of 6. Now, if you remember, let's say if B was some variable and G was some variable, which in our case it is, okay, it's boys and girls. So if we would expand this out, now we don't need to expand the entire thing out, okay? But this, you may recall that it gives us all the terms if we know the binomial expansion, right, in terms of the binomial theorem. Now, we want to have 4 girls. So really, the term that we're looking for from here is we want to have 4 girls, and then that means we're going to have 2 boys, right? And then, you may remember that in the binomial expansion, this was, there are 6 kids. So 6 choose, okay, and this would have been 4, and that 4 is because we wanted to have 4 girls. And if you set this question up like that, this really is just a question of saying, okay, well, you have 6 possible kids, and you want to choose 4 girls out of them, right? And then with that, so we can actually get exactly what this is, right? So this is 4 factorial, 2 factorial. I should know 6 choose 4. I think it's, maybe I'm wrong. Maybe is it 15? Maybe not. Let's just check it. So 6 times 5, that will be gone, divided by 2. Divided by 2, yeah, I'm way off here. So 3, oh no, so 3. This is 15. It was 15. So there's 15 possible ways. You can list all of them if you wanted to, but this is a nice quick way of being able to find that out if you've studied combinations and then the binomial theorem. Okay, so it's one application of that. Now the second part is, how about at least 1 girl? Okay. At least 1 girl. So anytime I see this at least 1, I always think, well, take total minus none, right? So none meaning that they were all boys. Well, they're all boys. There's only one way of doing that. That means you just have a boy. So that's going to be 1. Now the total number of possibilities, okay, that we could have, okay, within here, so within all of this, okay, is you can have a boy or a girl, okay, so those are 2 possibilities for each. So here, let me draw 1, 2, 3, 4, 5, 6, right? So it can be boy or girl. So we have two choices, right? We're assuming that it's 50%. You know, it's not swayed in any way. So 2, 2, 2, 2, 2, and 2. Okay, so this is, okay, so 2 basically to the 6. All right, so those are all the possibilities. So 1, 2, 3, 4, 5, 6. Yep, that's correct. And 2 to the 6, I guess, so it's that 64. So 63 with at least one girl. Okay, so that's what would have happened. So that, you know, at least one girl means one girl, or maybe two girls, or three girls, or four girls, or five girls, okay, or all the girls. So that's how we would set that up. Okay, so there you go. It's another counting one for you with possibilities. Okay, thanks for watching this one. Here's a nice example with just an expansion. You can approach this, you know, the brutal way of just expanding directly, or you can not necessarily cheat, but use a tool, which is the binomial expansion with the binomial theorem here. Okay, so what I will do, and I probably will do this, okay, if you've forgotten about the binomial theorem or expansion, maybe I'll put up a link up above there for you when you study combinations. And here, so the way that I would do it is, well, the 3, we can do that at the end. So just going to multiply all the terms because we want to expand and we want to simplify. And then we have, so 2a minus 5c squared to the 4. So let's assume, so this is my x, okay, this is going to be my y. So if you remember, x plus y, this is going to be to the 4, can be expanded by the binomial expansion. Okay, so I'll do this in kind of fast forward fashion to remind you, and then we'll try to simplify and collect all the terms. Okay, I'll see you right back. Okay, so I'll pause for just a moment just so that you can see. So that's the binomial expansion here. And then now I'm going to have to simplify this junk. Okay, so I'll do that next, okay, in fast forward fashion. And then we'll be right back to take care of this final 3 here that was in front. All right, so we're back here. So assuming I didn't make any kind of computation errors, so here are all the terms. So first one, second one, third one, fourth one, okay, and the last one there. So those are all of those, and then we can't forget, you know, to still multiply this by 3. So that's going to be, okay, spread across here, and we would then have to multiply all of this. Okay, so once we do that, we basically have the full out expansion of all of this. And so the binomial expansion is kind of useful. It still takes a little bit of time to try to do, but once you've learned your computations, or if you're still kind of utilizing Pascal's triangle, you can certainly do that to make your life a little bit easier in terms of the process to set this up. All right. Okay, so that's how we would have expanded. Again, I'm not going to bring the 3 inside because I think you can do that on your own. And then you would have the full out expansion, okay, and then the simplification of that as well. All right, so that's another one. Welcome to this example with regards to, I guess, a computation, okay, or combination example. So you are asked to create a portfolio of stocks. At present, you have a choice between picking from 6 bank stocks, 4 energy stocks, and 5 technology stocks. Maybe let's write that down. So here are my givens. So 6 Okay, bank stocks. 4 energy stocks. And then 5 technology stocks. How many 3 stock portfolios can you create? So 3 stock portfolios. That include at least 1 technology. Okay, so the key is 1 tech at least. All right, so let's take a look and see how we can figure this out. Well, at least 1. So you can certainly find out the total. So that would have been, total minus no technology stocks. You can certainly do that, right? So that's one way of approaching this question, because of the fact that it says at least 1. Well, the total, we have 6, 4, so that's 10, so that's 15, right? Different stocks, choose 3 of them. So because the order doesn't matter here. Okay, so that would have been the total number of 3 stock combinations that we could create. Now, with no technology stocks, we have to remove those, so that would have been 10, choose 3, which would have been just the banking and energy stocks, and we want to see how many 3 combinations we can make out of those. And then, so that would have been your answer. All right, so you can set this up like that. I guess another way you can set this up, if it says at least 1, so that means, you can have kind of cases, so case 1, then we're going to have to add them up. So if it's at least 1, so that, for instance, so we had 1, 2, 3, well, we have 5 technology stocks. So 5 choose 1, right? Because if that's at least 1, and then what does that leave you? It leaves you with, I guess, 10, right? So 10 choose 2. Okay, that's the remaining ones that you can do. You're going to have to multiply this out to find out. That's with 1 tech stock. So 1 tech. Case 2 would have been that you have, so 1, 2, 3. So you have 2. Let's say 5 choose 2. So that you have 2 technology stocks. Then that leaves you, 10 choose 1 of the remaining bank and energy. So that would have been case number 2. And then you would have to do case number 3, which is all 3 of them are technology stocks. So 5 choose 3, and then how many you have. And so for these, so this is, you can find what these are and then just add them up. So add your additive property, okay, for the counting, and that would have given you the total. I think this one is easier to be able to do, and you can compute both of these, right? And then just make sure that you actually, that they're equivalent, okay? So try that actually. So compute all of this, once you're working this out, depending on which path you took, but also try to compute this one and then add them up, and you'll see that they should be equivalent, all right? Because those are the 2 approaches that you could have used for this example. This was a nice example actually for thinking about combinations. All right, so thanks for watching this one. This example is a nice one with regards to trying to utilize Venn diagrams. So you have a high school. It has 2,345 students. It says from the set of students, 79 are interested in trying out for the swim team, 180 interested for the track and field team, 120 for volleyball team. Okay, so once I start seeing all of these different things, okay, let's try to write all of these things out. Okay, so given, and it says draw Venn diagram for part A. So, well, let's do that to make our life a little bit easier to map this whole thing out. It's not what I wanted. Okay, so we want to have a nice box here. Okay, so we have in total 2,345 students. Okay, and so it looks like we're gonna have 3 things. So here's my one. Let's duplicate these. Hopefully this will come out nicely. Okay, let's center it out. So, and let's label them. So it says, let's make the swim team, track and field, and then volleyball. All right. Okay, so we have 79 swim. Okay, so swim, 79. Track, 180. Okay, we'll fill all of this up shortly. 120 volleyball. Okay. Now they're also going to give us, so from the interested students, 50 of them are interested in swim and track. Okay, swim and track. Swim and track. I guess I can, well, technically I guess this is written like this, the number of. So swim and track, I said 50. So the number between, let's say, swim and volleyball, I guess we'll need that. And then track and volleyball. So let's see what they give us for those. Okay, 43 track and volleyball. 43 track and volleyball. And 33 swim and volleyball. So 33. And I guess we also need the intersection between all of these. And there are 20. Okay. So now drawing this out on a Venn diagram, always start internally from the most intersection. So that means, so this is, let me change color here. This is going to be 20. And now you can proceed in any direction that you like. Okay, so let's say swim and track. Okay, so that means 20. So if there's total of 50, so that means 30. This is going to be 30 between swim and track, because 30 plus 20 is the 50, right? Then swim and volleyball is 33. Swim and volleyball is 33 minus, so that's going to be 13. Okay, so we can have that. And I guess track and volleyball, 43, 20, so that's 23. Okay, and then now you can go ahead and, you know, keep moving on up. So if we had 79 here, so for swimming, so 79 minus, I guess, 30 minus 20 minus 23. Whoops, I added them. Minus 20 minus 23. Sorry, that's for swimming. So that's 30, 20, and 13. So that's 16 left there. Swimming. Then 180, that's for track, minus 30, minus 20, minus 23. So that's 107. So those ones are only interested in track. And then the last one, so 120 for volleyball. Looks like it's popular. Minus, so 13, minus 20, minus 23, 64. Okay. So there you go. So that would have been your Venn diagram, which means, I guess, so 2, 3, 4, 5, 4, 5. So notice that's the total, right? And then, so, from all of these, so if we would find out, okay, what the total is there, so on the inside, we can just add them all up, right? Okay, and then find out exactly how many we have, or we can use the addition. We can actually use all of this information right here. So we can add all of these, right? We would subtract all of these, and then we would have to add this one because we subtracted too many times. Okay, so that's with regards to Venn diagrams. And 3, I actually did also a nice video on this. Maybe I'll put up a link up above there. Okay, if you want another reference. So we've drawn a Venn diagram, and now how many students are not interested in any of the teams? Well, I mean, I can certainly do this all at once. So minus, okay, and then I'm going to open brackets. So I'm going to go through all of this. So 16 plus 30 plus 20 plus 13 plus 23 plus 107 plus 64. So those are all the ones inside. So there's still quite a lot of students that are not interested in any of it. Okay, so there you have it. So that would have answered this one. How many students are not interested in any of the teams? And then you can add them up if you wanted to know how many students are just interested in at least one team. Okay. All right, so that's a nice example of another Venn diagram for you. Okay, I hope that you found this useful. Thanks for watching. See you in a future video. Bye, everybody.